This is the EdExcel A-Level Further Maths Paper 1 covering the Core Pure module, and it's from the June 2024 series. Question number 1. f of z equals z to the 4 subtract 6z cubed plus az squared plus bz plus 145, where a and b are real constants. Given that 2 plus 5i is a root of the equation f of z equals 0, part A, determine the other roots of the equation f of z equals 0. Now we know that if we've got one of the roots being a complex number, the other root will be the complex conjugate. So, if z1 equals 2 plus 5i is a root of f of z equals 0, that means then z2, which is equal to 2 subtract 5i, the complex conjugate of 2 plus 5i, is also a root of f of z equals 0. Now, we've got a polynomial of degree 4 here, and we know two of the roots, 2 plus 5i and 2 subtract 5i. So we can rewrite f of z equals 0 as follows. We've got z subtract the root 2 plus 5i multiplied by z subtract the other root 2 subtract 5i, and we need to multiply this by a quadratic z squared plus cz plus d, and we set this equal to 0. We've got this bracket multiplied by this bracket, which gives us a quadratic, so we have a quadratic multiplied by another quadratic, which will give us a polynomial of degree 4. So the bracket here we can rewrite as z subtract 2 subtract 5i, and the bracket here we can rewrite as z subtract 2 plus 5i, and we still have this bracket here, z squared plus cz plus d, and this is equal to 0. Z subtract 2 subtract 5i multiplied by z subtract 2 plus 5i, here we have a difference of 2 squares. So we can rewrite this as z subtract 2 squared, and then we have negative 5i multiplied by positive 5i, which is positive 25. And we multiply this by z squared plus cz plus d, and we set this equal to 0. Z subtract 2 squared plus 25, that is z squared subtract 4z plus 29, and we multiply this by z squared plus cz plus d, and this is equal to 0. And what we need to do is find out what c and d are, and we can do that by comparing coefficients. So we need to compare this with this over here. So let's take a look at the z cubes. If we take a look at what gives us a z cube, we have z squared multiplied by cz. The coefficient of z cubed then will just be c, and then we have negative 4z multiplied by z squared. That gives us a z cubed, so the coefficient of z cubed will be negative 4. And if we take a look here, we've got negative 6z cubed, so the coefficient of z cubed is negative 6. Meaning, we set this equal to negative 6, and if I solve, c is equal to negative 2. Let's now take a look at the numbers. For the numbers, we multiply 29 by d, and you can see here we've got 145. So we set this equal to 145, meaning d is equal to 5. And therefore, we can rewrite the result here. We can rewrite it as z squared subtract 4z plus 29 multiplied by z squared subtract 2z plus 5. And of course, it's equal to 0. From this equation, we have z squared subtract 4z plus 29 equals 0. And from this equation, we have z squared subtract 2z plus 5 equals 0. If I solve z squared subtract 4z plus 29 equals 0, we know, because we've got z1 equaling 2 plus 5i, and we've got z2 equaling 2 subtract 5i, and from that we found this equation, the equation here would have solutions z equals 2 plus minus 5i. We can now use our calculator to solve z squared subtract 2z plus 5 equals 0. From our calculator, let's go to the equation sub-menu. We have a polynomial of degree 2. Let's change the calculator settings to display complex numbers. We have z squared subtract 2z plus 5 equals 0. So we've got one of the roots being 1 plus 2i and the other root being 1 subtract 2i, meaning z is equal to 1 plus minus 2i. So the polynomial of degree 4, when we set that equal to 0, we get solutions of z equals 2 plus minus 5i and z equals 1 plus minus 2i. Part B, show all the roots of f of z equals 0 on a single Argand diagram. As coordinates, we can write these roots as 2, 5, 2, negative 5, 1, 2, 1, negative 2. And therefore we can plot these on an Argand diagram. That is what we see here. Question number 2. The roots of the equation 2x cubed subtract 3x squared plus 12x plus 7 equals 0 are alpha, beta and gamma. Without solving the equation, part A, write down the value of each of alpha plus beta plus gamma, alpha beta plus alpha gamma plus beta gamma, and alpha beta gamma. We can rewrite the cubic as x cubed subtract 3x squared over 2 plus 6x plus 7 over 2 equals 0. We've divided the equation here by 2, and in doing so we end up with this equation shown here. And so for part A, alpha plus beta plus gamma, that will equal negative 3 over 2, which is 3 over 2. Alpha beta plus alpha gamma plus beta gamma, that's equal to 6, and alpha beta gamma is equal to negative 7 over 2. Part B. Use the answers to part A to determine the value of the following. For the first part, we have 2 over alpha plus 2 over beta plus 2 over gamma. 2 over alpha plus 2 over beta plus 2 over gamma, that's equal to 2 multiplied by alpha beta plus alpha gamma plus beta gamma all over alpha beta gamma. And therefore we have 2 multiplied by 6 over negative 7 over 2. And that's equal to negative 24 over 2. Next, we have to determine the value of alpha subtract 1 multiplied by beta subtract 1 multiplied by gamma subtract 1. Alpha subtract 1 multiplied by beta subtract 1 multiplied by gamma subtract 1, well, we can multiply the alpha subtract 1 and the beta subtract 1 together. That would give us alpha beta subtract alpha subtract beta plus 1, and we multiply this by gamma subtract 1. And so we have alpha beta times gamma, then we have alpha beta multiplied by negative 1, then we have negative alpha multiplied by gamma, then we have negative alpha multiplied by negative 1, then we have negative beta multiplied by gamma, then we have negative beta multiplied by negative 1, then we have 1 multiplied by gamma, and then we have 1 multiplied by negative 1. And so we can rewrite this as alpha beta gamma subtract alpha beta plus alpha gamma plus beta gamma plus alpha plus beta plus gamma subtract 1. Using the results from part A, we would have negative 7 over 2 subtract 6 plus 3 over 2 subtract 1, and that's equal to negative 9. We now have to determine the value of alpha squared plus beta squared plus gamma squared. Alpha squared plus beta squared plus gamma squared is equal to alpha plus beta plus gamma squared subtract 2 multiplied by alpha beta plus alpha gamma plus beta gamma. So we have 3 over 2 squared subtract 2 multiplied by 6, and working this out we get negative 39 over 4. Question number 3. Figure 1 shows the design for a bathing pool. The pool P, shown unshaded in figure 1, is surrounded by a tiled area T, shown shaded in figure 1. The tiled area is bounded by the edge of the pool and by a circle C with radius 6 meters. The center of the pool and the center of the circle are the same point. The edge of the pool is modeled by the curve with polar equation r equals 4 subtract a times sine of 3 theta, where theta is in between 0 and 2 pi, and a is a positive constant. Given that the shortest distance between the edge of the pool and the circle C is 0.5 meters, part A, determine the value of A. We know the circle has a radius 6 meters, and we know the shortest distance between the edge of the pool and the circle is 0.5 meters. Here is the circle, here is the edge of the pool, the radius of the circle is 6, the distance here is 0.5, so the distance from the center to the edge of the pool is 5.5 meters. The maximum value of r is 5.5, and we can find the maximum value of r by considering this equation. If I think about this sine 3 theta, I know sine 3 theta is bounded between negative 1 and 1. And because I've got r equals 4 subtract a sine 3 theta and a is a positive constant, for me to find the maximum value of r, I need to recognize the maximum value of r occurs when sine 3 theta equals negative 1. So we have r max, which is equal to 4 subtract a multiplied by negative 1, and we set this equal to 5.5, which is the distance from the centre to the edge of the pool. And if I solve for a, you will find a to equal 1.5, and so therefore we can conclude r is equal to 4 subtract 3 over 2 sine 3 theta. 1.5 is the same as 3 over 2. Part B. Hence, using algebraic integration, we have to determine according to the model the exact area of T. We've got this circle and we've got the pool shown here. The area of T will be the area of the circle subtract the cross-sectional area of the pool. The area of the circle, that's just going to be pi times by the radius 6 squared, which is 36 pi. We can now find the area of the pool. We know the area of a sector is given by a half times the integral of r squared d theta. So we have a half times the integral of r squared d theta in between 0 and 2 pi. We already know what r is. That's 4 subtract 3 over 2 sine 3 theta. So we have a half times the integral from 0 to 2 pi of 4 subtract 3 over 2 sine 3 theta squared d theta. So I've got a half times the integral from 0 to 2 pi of 16 subtract 12 sine 3 theta plus 9 over 4 sine squared 3 theta d theta. Now, what we know from the known identities is cos 2x is equal to 1 subtract 2 sine squared x, meaning sine squared x is equal to 1 subtract cos 2x over 2. And so, sine 3 theta squared will equal 1 subtract cos 6x over 2. The reason this is useful is because we can rewrite the result here into a more integrable form. So we've got a half times the integral from 0 to 2 pi of 16 subtract 12 sine 3 theta plus 9 over 4 multiplied by sine squared 3 theta, which is the same as 1 subtract cos 6x over 2 d theta. So I've got half times the integral from 0 to 2 pi of 16 subtract 12 sine 3 theta, and then I've got 9 over 8. That comes from 9 over 4 times 1 half, and then I've got 9 over 4 multiplied by negative cos 6 theta over 2, which is negative 9 cos 6 theta over 8. And so, if we combine the 16 and the 9 over 8, we end up with 137 over 8. So I've got the 1 half times the integral from 0 to 2 pi of 137 over 8, subtract 12 sine 3 theta, subtract 9 cos 6 theta over 8 d theta. So let's evaluate this. I've got the 1 half, and if I integrate 137 over 8, I've got 137 theta over 8. If I integrate negative 12 sine 3 theta, I end up with 4 cos 3 theta. If I integrate negative 9 cos 6 theta over 8, I end up with negative 3 sine 6 theta over 16. We wish to evaluate this from 0 to 2 pi. If I multiply the half into the bracket, I've got 137 theta over 16 plus 2 cos 3 theta subtract 3 sine 6 theta over 32, evaluated from 0 to 2 pi. So Substituting in for our upper limit, we've got 137 times 2 pi over 16 plus 2 cos of 3 times 2 pi, subtract 3 sine of 6 times 2 pi over 32. For our lower limit, we've got 137 times 0 over 16 plus 2 cos of 3 times by 0, subtract 3 sine of 6 times 0 over 32. And therefore we end up with 137 pi over 8. So the area of T will equal 36 pi subtract 137 pi over 8, which is equal to 151 pi over 8 meters squared. Question number 4. The complex number z equals e to the I theta, where theta is real. Part A, show that z to the n plus 1 over z to the n is equivalent to 2 cos n theta, where n is a positive integer. For part A, we have z to the n plus z to the negative n. And knowing that z is equal to e to the I theta, we have z to the n, which is then e to the I theta to the n, and z to the negative n, that will be e to the I theta to the negative n. So we have e to the I n theta plus e to the negative I n theta. E to the I n theta, that is cos n theta plus I sin n theta, and e to the negative I n theta, that is cos of negative n theta plus I sin of negative n theta. This bit will remain the same as cos n theta plus I sin n theta, and cos of negative n theta, because cos is an even function, that is the same as cos n theta, and because sine is a odd function, I sin of negative n theta, that is negative I sin of n theta. And if we add these together, I sin n theta subtract I sin n theta is 0, cos n theta plus another cos n theta, that will be 2 cos n theta, and that is the result we wanted to show. Part B. Show that cos theta to the 5 is a 16th of cos 5 theta plus 5 cos 3 theta plus 10 cos theta. To begin with, let's see what happens when n equals 1. When n is equal to 1, we have z plus 1 over z, which will equal 2 cos theta, and that's using the result from part A. And so, z plus 1 over z to the 5, that will equal 2 cos theta to the 5. The reason I'm doing this is because when I work out 2 cos theta to the 5, I will be left with something involving a cos theta to the 5. So we have z plus 1 over z to the 5, which is 32 cos theta to the 5. Now, this z plus 1 over z to the 5, we can use the binomial expansion. So we have 5 choose 0 times by z to the 5 times by 1 over z to the 0 plus 5 choose 1 times z to the 4 times 1 over z to the 1. Then we have 5 choose 2 times z to the 3 times 1 over z squared plus 5 choose 3 times z squared times 1 over z cubed plus 5 choose 4 times z to the 1 times 1 over z to the 4 plus 5 choose 5 times z to the 0 times 1 over z to the 5. For the first term, that will simplify to z to the 5, For the next term, that will simplify to 5 z to the 4 times 1 over z. For the next term, that will be 10 z cubed times 1 over z squared. For the next term, we've got 10 z squared times 1 over z cubed. For the next term, we've got 5 times z times 1 over z to the 4. For the next term, we would simply have 1 over z to the 5. So we have z to the 5. Now we've got 5z to the 4 times 1 over z. That's going to be 5z cubed. And then we've got 10z cubed times 1 over z squared. That's 10z. Then we have 10z squared times 1 over z cubed. That will be 10 times 1 over z. Then we have 5 times z times 1 over z to the 4. That will be 5 times 1 over z cubed. And then we have 1 over z to the 5. And if we group together the terms which are similar, well, we've got the z to the 5 and the 1 over z to the 5. And then we've got the 5z cubed and the 5 times 1 over z cubed. So that will be 5 times z cubed plus 1 over z cubed. And then we have 10z plus 10 times 1 over z. So that will be 10 times z plus 1 over z. And what we now need to do is use this result here. So z to the 5 plus 1 over z to the 5, that will be 2 cos 5 theta. Then I've got 5 times by z cubed plus 1 over z cubed, so that will be 2 cos 3 theta. Then I've got 10 times by z plus 1 over z, so that will be 2 cos theta. So I've got 2 cos 5 theta plus 10 cos 3 theta plus 20 cos theta. And this is what z plus 1 over z to the 5 is, which is the same as 32 cos theta to the 5. So this result is what 32 cos to the 5 theta is. And now if I divide by 32, we can conclude cos theta to the 5 is cos 5 theta plus 5 cos 3 theta plus 10 cos theta over 16. Part C. Hence, make your reasoning clear. Determine all the solutions of cos 5 theta plus 5 cos 3 theta plus 12 cos theta equals 0 in the interval 0 to 2 pi. We have this equation cos 5 theta plus 5 cos 3 theta plus 12 cos theta equals 0. And we know from part B that 16 cos theta to the 5 is equal to cos 5 theta plus 5 cos 3 theta plus 10 cos theta. So we can rewrite this equation using what we found in part B. We would have cos 5 theta plus 5 cos 3 theta plus 10 cos theta. Here we've got a 12 cos theta, so I add on 2 cos theta, and that's equal to 0. So 10 cos theta plus 2 cos theta, that is 12 cos theta. Cos 5 theta plus 5 cos 3 theta plus 10 cos theta, that is 16 cos theta to the 5, and then we add on this 2 cos theta, this is equal to 0. And dividing through by 2 and then factorising out a cos theta, we have cos theta multiplied by 8 cos theta to the 4 plus 1 equals 0. So we've got cos theta equaling 0, or 8 cos theta to the 4 plus 1 equals 0. Now if I think about cos theta equaling 0, from here theta will equal pi over 2, or 3 pi over 2. And if I think about 8 cos theta to the 4 plus 1 equaling 0, cos theta to the 4 will always be greater than or equal to 0. So we've got something greater than or equal to 0 plus 1. This will always be greater than 0. So this equals 0 is not true, meaning we've got no solutions for 8 cos theta to the 4 plus 1 equaling 0, meaning theta is equal to pi over 2 and 3 pi over 2 only. Question number 5. A raindrop falls from rest from a cloud. The velocity v meters per second vertically downwards of the raindrop t seconds after the raindrop starts to fall is modelled by the differential equation t plus 2 times dv over dt plus 3v equals k times t plus 2 subtract 3, where t is greater than or equal to 0 and k is a positive constant. Part A, we have to solve the differential equation to show that v equals k over 4 times t plus 2 subtract 1 plus 4 times 2 subtract k over t plus 2 cubed. We begin with the differential equation. Our next step is to divide each term by t plus 2, and in doing so we have dv over dt plus 3 over t plus 2 times v equals k subtract 3 over t plus 2. Now, to solve this first order differential equation, we need to recognise it's of the form dy over dx plus py equals q, where p and q are functions of x. This has a solution of e to the power of p with respect to x times y equals the integral of e to the power of the integral of p with respect to x times q dx plus c, where the integrating factor is equal to e to the power of p with respect to x. What we can do is work out what the integrating factor is, and the integrating factor would have to look at the coefficient of v, and so the integrating factor is equal to e to the power of the integral of 3 over t plus 2 with respect to t. So let's work this out. We have e to the power of 3 times the natural log of t plus 2, which is e to the power of the natural log of t plus 2 cubed, which simplifies to t plus 2 cubed. And so we would have a solution of t plus 2 cubed times v equals the integral of t plus 2 cubed times by k subtract 3 over t plus 2 with respect to t plus c. So on the left hand side we've got t plus 2 cubed times v, and on the right hand side we've got t plus 2 cubed times by k, then we've got t plus 2 cubed multiplied by negative 3 over t plus 2, and we add on the constant c. So on the left hand side we've got t plus 2 cubed v equals, and on the right hand side if I integrate k times t plus 2 cubed, we end up with k times t plus 2 to the 4 over 4, and if I integrate negative 3 times t plus 2 squared, we end up with negative t plus 2 cubed, and we add on a constant c. If I divide each term by t plus 2 cubed, we end up with v equals, well, if I divide this by t plus 2 cubed, we end up with k times t plus 2 over 4, and if I divide this by t cubed, we end up with negative 1, and then we have c over t plus 2 cubed. We have the condition t equals 0, v equals 0, so we substitute this into here. So we replace the t with 0 and we replace the v with 0, so we have 0 equals k times by 2 over 4 subtract 1 plus c over 2 cubed. So we have 0 equals k over 2 subtract 1 plus c over 8, and if I multiply through by 8, I have 0 equals 4k subtract 8 plus c, and therefore c will equal 4 times 2 subtract k. I can replace this c with 4 times 2 subtract k, and in doing so we end up with v equals k times by t plus 2 over 4 subtract 1 plus 4 times 2 subtract k over t plus 2 cubed. This is our general solution. Question number 6. Prove by induction that for all positive integers n, the sum of 2r subtract 1 squared from r equals 1 to r equals n is equal to a third n times 4n squared subtract 1. It's always useful to write down what we want to show. We want to show that the sum of 2r subtract 1 squared from r equals 1 to r equals k plus 1 is equal to k plus 1 times 4 times k plus 1 squared subtract 1 all over 3. We replace the n with k plus 1. Our first step is to see what happens when n is equal to 1. On the left hand side, we've got the sum from r equals 1 to r equals 1 of 2r subtract 1 squared, so that's 2 times by 1 subtract 1 squared, which is equal to 1. And on the right hand side, we have 1 times by 4 times by 1 squared subtract 1 all over 3, and that's equal to 1. Because the left hand side and the right hand side are equal, the result is true for n equals 1. Our second step is to assume that this result is true for n equals k. So we replace the n with k. That's to say, the sum from r equals 1 to r equals k of 2r subtract 1 squared is equal to k times by 4k squared subtract 1 over 3. Our third step, which is the induction step, we need to prove that the result is true for n equals k plus 1. So I've got the sum from r equals 1 to r equals k plus 1 of 2r subtract 1 squared. So what this is equal to is the sum of the first k terms, as we see here, plus the k plus 1th term. And the k plus 1th term is when we replace the r with k plus 1. So I've got 2 times k plus 1 subtract 1 squared. What we can now do is use the induction step. So this will become k times by 4k squared subtract 1 over 3 plus 2 times k plus 1 subtract 1 squared. And we need to go from here to here. So this term stays the same, and then 2 times k plus 1 subtract 1 squared, that is the same as 2k plus 1 squared. So this term stays the same, and 2k plus 1 squared, that is 4k squared plus 4k plus 1. This term stays the same, and I'm going to rewrite this so that we've got a denominator of 3, and so for the numerator we'd have 12k squared plus 12k plus 3. This simplifies to 4k squared plus 4k plus 1. If I take out a 1/3 as a factor, we would have a third times by k times 4k squared subtract 1 plus 12k squared plus 12k plus 3. And so if we simplify inside the bracket, we would have 4k cubed plus 12k squared plus 11k plus 3. We need to somehow factorize this. And the way we can do that is to use the cubic solver on our calculator and then work backwards. from our calculator, let's go to the equation solver. We have a polynomial of degree 3. We've got 4k cubed plus 12k squared plus 11k plus 3 equals 0. So we've got k equaling -1/2, -1 and -3 over 2. Meaning when we factorise this, we would have k plus 1 times 2k plus 1 times 2k plus 3. Now if we look at what we wish to show, here you can see we've got a k plus 1 over 3, and then we've got this 4 times by k plus 1 squared subtract 1. So I've got this third, and then I've got this k plus 1, and then I'm going to multiply these two brackets together. So I've got 4k squared plus 8k plus 3. And if you remember from the show that, we have 4 times by k plus 1 squared subtract 1. It looks like a completed square form. And that's what I'm going to do. I've got this third times by k plus 1. And then this 4k squared plus 8k plus 3, I'm going to complete the square of it. So I've got 4 times by k squared plus 2k plus this 3. So I've got a third times by k plus 1. And then I've got 4. And then the k squared plus 2k, I can write that as k plus 1 squared subtract 1. And then I add on this 3. So I've got a third times by k plus 1, and then here we've got 4 times by k plus 1 squared subtract 1, and that's because 4 times -1 plus 3 gives us the -1. And so we have k plus 1 over 3 multiplied by 4 times k plus 1 squared subtract 1, and that is the result we wanted to end up at. So for our fourth step, which is the conclusion step, if it's true for n equals k, then it has been shown true for n equals k plus 1. And as it's true for n equals 1, the statement is true for all positive integers of n. Question number 7. The line L1 has equation r equals I subtract 2j plus 3k plus lambda times 2i plus j subtract 4k, and the line L2 has equation r equals 5i plus pj subtract 7k plus mu times 6i plus j plus 8k, where lambda and mu are scalar parameters and p is a constant. The plane pi contains L1 and L2. Part A, we have to show that the vector 3i subtract 10j subtract k is perpendicular to pi. We know what the equation of L1 is, and we know what the equation of L2 is. So we can state the direction vectors of L1 and L2, and we can state those to be n1, which is 2i plus j subtract 4k, and n2, 6i plus j plus 8k, respectively. Now what we need to do in this question is show that this vector 3i subtract 10j subtract k is perpendicular to pi. Now because pi contains L1 and L2, in other words L1 and L2 lie on pi, if we somehow show that this vector here is normal to n1 and this vector here is normal to n2, we would show then that 3i subtract 10j subtract k is perpendicular to pi. So let's do that vector 3i subtract 10j subtract k dot with n2, which is 2i plus j subtract 4k. Let's work this out. Well, we have 3 times by 2, negative 10 times by 1, and negative 1 times by negative 4. It turns out we get 0. And if I do this vector, dot with n2, which is 6i plus j plus 8k, we would have 3 times by 6, negative 10 times by 1, and negative 1 times by 8. It turns out here we get 0. So, as the dot product is 0, and as L1 and L2 also lie on the plane, we can therefore conclude that this vector 3i subtract 10j subtract k is perpendicular to pi. Part B. Hence determine a Cartesian equation of pi. We know already the normal vector to the plane pi. That's 3i subtract 10j subtract k. So pi would have an equation of the form 3x subtract 10y subtract z equals d, and we need to find out what d is. We know that the point 1, negative 2, 3 would lie on L1. And we know that L1 lies on pi. So we can substitute in this point into here. So we have 3 times by 1, subtract 10 times by negative 2, subtract 3 equals d. So d is equal to 20, meaning pi would have equation 3x subtract 10y subtract z equals 20. Part C, hence determine the value of p. This time we can use the line L2, and what we know is 5p and negative 7 lies on L2. We know so far pi has equation 3x subtract 10y subtract z equals 20, and this point 5p negative 7 lies on L2, and we know that L2 lies on pi, so we can substitute in this point into the equation. We have 3 times by 5, subtract 10 times by p, subtract negative 7 equals 20. 10p is equal to 2, so p is equal to 1/5. Given that the lines L1 and L2 intersect at the point A, and the point B has coordinates 12, negative 11, 6, part D, determine to the nearest degree the acute angle between AB and pi. Before we do anything else, we can state the equation of L1 and L2 in column form, knowing what p is, which is 1/5. So the line L1, that's got equation r equals 1, negative 2, 3 plus lambda times by 2, 1, negative 4, and the line L2 has equation 5, 1/5, because that's what p is, negative 7, plus mu times by 6, 1, 8. And we know that the point of intersection of L1 and L2 is A, which I'm going to give general coordinates x, y, and z. So if I think about some general point on L1, 1 plus 2 lambda, negative 2 plus lambda, and 3 subtract 4 lambda will lie on end wall. And similarly, 5 plus 6 mu, 1/5 plus mu, negative 7 plus 8 mu lies on L2. Now, because these two lines intersect, we can find out two equations by setting the x's equal to each other and the z's equal to each other. So if I equate the x's, I've got 1 plus 2 lambda equals 5 plus 6 mu. So 2 lambda subtract 6 mu is equal to 4. And if I equate the z's, I would have 3 subtract 4 lambda equals negative 7 plus 8 mu, from which we can see 4 lambda plus 8 mu is equal to 10. Let's solve these equations simultaneously. We have 2 lambda, subtract 6 mu equals 4, and 4 lambda plus 8 mu equals 10. So I've got lambda equals 2.3, and I've got mu which is equal to 0.1. At this point, it would be a good idea to sketch the situation. We've got the plane, and we've got the normal to the plane, which is given by 3i subtract 10j subtract k. We've got the line L1 and L2 which lie on the plane, and the point A is the intersection of L1 and L2. We've got some point B, and if I join A and B together, what we need to do is find out the angle in between this line segment and the plane pi. So before we do anything else, let us find that point A. So we need to use this and this with our values of lambda and mu to help us find out what A is. So A, that will be using the value of lambda, 1 plus 2 times by 2.3, negative 2 plus 2.3, 3 subtract 4 times by 2.3, so we get 5.6, 0.3 and negative 6.2. And if I check with the value of mu, A, that's given by 5 plus 6 times 0.1, a fifth plus 0.1, negative 7 plus 8 times by 0.1, which is 5.6, 0.3 and negative 6.2. Because we've got the same values for A, we can therefore conclude we've got coordinates 5.6, 0.3, negative 6.2. Now our next step would be to find out this vector AB, because we want to find the angle between AB and the plane. AB, that's OB take away OA, so I've got OB, which is 12i subtract 11j plus 6k, subtract OA, which is 5.6i plus 0.3j subtract 0.62k. And working this out, we get 6.4i subtract 11.3j plus 12.2k. This is what the vector AB is. Now let's draw this as a section drawing. We see this. We've got this plane pi, we've got the point A where the line joining AB intersects the plane, and then we've got this normal vector. We need to work out what alpha is, and we can do that using this formula here. AB dot with n is equal to the magnitude of AB times the magnitude of n times cos alpha. So we've got AB, which is 6.4i subtract 11.3j plus 12.2k, dot with 3i subtract 10j subtract k, equals the magnitude of AB, which is the square root of 6.4 squared plus negative 11.3 squared plus 12.2 squared, times by the magnitude of n, which is 3 squared plus negative 10 squared plus negative 1 squared, times by cos alpha. So on the left hand side, I've got 6.4 times by 3 plus negative 11.3 times by negative 10 plus 12.2 times by negative 1. And on the right hand side, let's work out. We've got the square root of 6.4 squared plus 11.3 squared plus 12.2 squared. Let's store this into A. So I've got 17.8, etc. And then I've got the square root of 3 squared plus 10 squared plus 1 squared which is equal to 10.4, etc. And I times this by cos alpha. So let us store that into B. And let's work out what the left hand side is. We have 6.4 times 3 plus negative 11.3 times by negative 10 plus 12.2 times by negative 1, so we get 120, and that's equal to, well, if I do A times by B, we get 186.8, etc. times by cos alpha. And so if I do 120 divided by this value here, cos alpha is equal to 0.6, etc. Now, for me to find out what alpha is, let's make sure our calculator is in degrees. And so we have the inverse cosine of this 0.6, which is equal to 50 degrees. So alpha is 50 degrees. That's the angle between that line and the plane pi. Question number 8. A scientist is studying the effect of introducing a population of type A bacteria into a population of type B bacteria. At time t days, the number of type A bacteria x and the number of type B bacteria y are modelled by the differential equations dx over dt equals x plus y, dy over dt equals 3y subtract 2x. Part A, show that d squared x over dt squared subtract 4 dx over dt plus 5x equals 0. To begin with, we can call this first equation equation 1 and the second equation equation 2. What we need to do is end up with a d squared x. So we need to eliminate the y's. So if I take a look at the first equation, we can rearrange to say that y is equal to dx over dt subtract x, which I'll call equation 3. Now, because I want to show I've got a d squared x, it would make sense that I differentiate equation 1, because differentiating dx over dt with respect to t will give me a d squared x over dt squared. So differentiating 1, we have dx over dt plus dy over dt, which I will call equation 4. And now I will substitute in equation 2 into equation 4, and this will eliminate the dy over dt. So I've got d squared x over dt squared equals dx over dt plus 3y subtract 2x, which I'll call equation 5. And now I can substitute in this third equation into equation 5. So I have d squared x over dt squared equals dx over dt plus 3 times by dx over dt subtract x. That's what y is, as we see here, subtract 2x. And if we tidy this up, we've got d squared x over dt squared subtract 4dx over dt plus 5x equals 0, which I'll call equation 6. And that's what we wanted to show. Part B, determine a general solution for the number of type A bacteria at time t days. The first thing we can do is form an auxiliary equation. In doing so, we have m squared subtract 4m plus 5 equals 0. And if I solve this equation, you will find m to equal 2 plus minus I, meaning the general solution is given by e to the 2t multiplied by a cos t plus b sin t, which I will call equation 7. We now need to find a general solution for y. We know what y is, that's dx over dt subtract x. So we've just worked out what the general solution for x is, so we need to differentiate what we've just found and then subtract x. So, if I differentiate equation 7 to find dx over dt, we can use the product rule. So, we've got u and v, so I've got v times by u dash plus u multiplied by v dash. So I've got e to the 2t multiplied by 2a plus b cos t plus 2b subtract a sin t, which I will call equation 8. And we now need to substitute in equation 7 and equation 8 back into equation 3. So y general solution is then equal to e to the 2t times 2a plus b cos t plus 2b minus a sin t minus e to the 2t times a cos t plus b sin t. And if I tidy this up, we end up with e to the 2t multiplied by a plus b cos t plus b subtract a sin t, which I will call equation 9. The model predicts that at time t hours the number of bacteria in the two populations will be equal. Given that x equals 100 and y equals 275 when t equals 0, part D, determine the value of t giving an answer to 2 decimal places. So when t equals 0, x is equal to 100. So what I need to do is substitute this into equation 7. So I've got 100 equals e to the 0 times a cos of 0 plus b sin of 0. I know that cos of 0 is just 1, so I've got a which is equal to 100. Now we can substitute in the condition t equals 0, y equals 275 into equation 9. So I've got 275 equals e to the 0 multiplied by a plus b cos of 0 plus b subtract a sin of 0. I know that a is equal to 100, so I've got 275 equals e to the 0 times 100 plus b cos 0 plus b subtract 100 sin of 0, and sin of 0 is just 0. So I've got 275 equals, well, e to the 0 is just 1 and cos of 0 is 1, so I've got 100 plus b. And that means b is equal to 175. So now we can state the particular solution. For x particular solution, we know what a is, we know what b is. That's 100 and 175 respectively. So the particular solution for x is e to the 2t multiplied by 100 cos t plus 175 sin t. And for the particular solution for y, we know what a and b are. So we have e to the 2t multiplied by 100 plus 175 cos t plus 175 take away 100 sin t. And this simplifies to e to the 2t times 275 cos t plus 75 sin t. We know that these equations 10 and 11 are equal when t equals t, so we need to set them equal to each other. So I've got x, which is e to the 2t times 100 cos t plus 175 sin t, and this is equal to e to the 2t times 275 cos t plus 75 sin t. Now, the e to the 2t's cancel on both sides, and if we rearrange, we will be left with 100 sine t equals 175 cos t. And so, rearranging this equation, we see that tan t is equal to 7 over 4. So now we can solve to find out what t is. We have the inverse tangent of 7 over 4, which is 1.05, etc. And if you recall from the question, t is in days, and here we have hours. So let's multiply this by 24. You will see t is equal to 25.54 hours. Part E. Suggest a limitation of the model. Here, the model is not valid whenever it predicts negative populations, so that is a limitation of the model.